morning? Isn't this a lovely day for chemistry? Yes, yes, yes. It's a lovely day for chemistry. You know, I don't know if you attended Hazmat Module 1A and 1B under Dieter Heinz. He always starts his lecture with, "What a wonderful day for chemistry." And it's stuck in my mind, so that's why I use it. So I'm sorry for Dieter because I'm using his line. But anyway, welcome to Chemistry for CUPA Inspectors. And actually, I applaud you because chemistry is not a very popular topic. And yet you're here. And I appreciate that. Thank you very much. So we'll just begin. This entire presentation might just be pure review for most of you. But to some of you, it might be just going over your head. But I hope my objective for this presentation is that you learn just a few things here and there, because I'm pretty sure that most of the things that I'm going to be saying you already know. And you just jog your memories. To some of you, you'll need a few jogging of your memory before you can actually stick it. But to some of you, it's already there. Some of you might already also be able to teach this course, okay? So just be patient. And I'm pretty sure the latter part of the session, which is the case studies, will be more exciting, okay? I promise that. I mean, the theory is not that interesting, but I'll try and make it interesting for you, right? Because it's a wonderful day for chemistry. Yes. Well, we start with the basic chemistry review. And when we do basic chemistry review, you have to understand what the definition of chemistry is. Chemistry is the study of matter. And everybody knows what matter is, right? Anything that occupies space and has mass. That's from 8th grade or 7th grade. Actually, my daughter is in 4th grade and she's already studying something like that, but it's too advanced. Anyway, it's the study of matter and the changes it undergoes. Matter can be subdivided into pure substances and mixtures. Under mixtures, you have heterogeneous mixtures, suspensions, solutions. Under pure substances, you have elements and compounds. All these 5 subdivisions of matter, as CUPA inspectors, we encounter them. As CUPA inspectors, all the different types of substance matter we encounter. Heterogeneous mixtures are like anything that, if you take a portion on this side and take another portion on this side, and when you compare them, they're not the same. That's heterogeneous mixture, okay? Suspensions are dispersed particles in a dispersing medium, like colloids. Heterogeneous mixtures, there's a lot of examples. But for suspensions, for CUPA inspectors, most of your inks, pigmented inks, they are suspensions. If you don't know that, sorry, but they are suspensions. They're colloidal suspensions. Eventually, if you filter them out, it's going to come out. The solids are going to come out, okay? But they're actually suspended in the dispersing medium. Solutions, of course, you come across solutions all the time, all right? Compounds and elements are pure substances. Now, matter has so many properties, and the only way we can classify them is either physical or chemical. Physical properties describes the response of the substance to some external influence, such as heat, light, force. Examples of physical properties, anybody? Color. Color is correct. Size, density, boiling point, flash points. Those are physical properties. Chemical properties describes the interaction of the substance with another. Those are electronegativity, heats of fusion, paramagnetism, things like that. Those are the chemical properties. It's the interaction of the substance with another. But as a CUPA inspector, what type of properties actually do we see on the MSDSs? On the MSDSs, what's really interesting is that sometimes you will, some RP would say, oh, it has a high vapor pressure, or it has a low vapor pressure. And you know that vapor pressure is the tendency of the material to vaporize, right? Say yes. Yes, thank you. Thank you, by the way. So that's the vapor pressure. It's actually the pressure exerted by the gas or the vapor molecule that it exerts to the liquid when it turns back to liquid. It's in equilibrium. equilibrium with the vapor and the liquid phase. Okay, so that's the pressure exerted by the gas, by the vapor molecule. But for CUPA inspectors, all you need to know is that vapor pressure is the tendency to vaporize. So if you come across a facility, you're inspecting a facility, and then you find that there's a small spill somewhere in the storage area of hazardous material, and then you ask for the MSDS for that material, and you see that it has a vapor pressure of, say, 250 millimeters mercury. Is that a high vapor pressure? Is that a low vapor pressure? Now, this will help. Now, this numbers I use when I was an inspector, and it was very helpful. I'm sorry if I'm touching the microphone. Sorry for that. At 20 degrees centigrade, water has a vapor pressure of 18 millimeters mercury. Everybody knows the tendency of water to vaporize, right? You know how long it takes for water to just disappear, right? So the vapor pressure at 20 degrees, oh, by the way, 20 degrees is room temperature. Well, most books say 20 degrees centigrade is the room temperature, the ambient temperature, but some books, especially the Asian books, I'm Filipino, by the way, so that's why I have Asian books. They're 25 degrees centigrade, but 20 degrees centigrade is 68 degrees Fahrenheit, and that's the usual room temperature, especially in LA, I guess. We're always 70 degrees all throughout. That's why there's 10 million people in LA because of the weather. Water has a vapor pressure of 18 millimeters mercury, all right? So if you compare the the vapor pressure of the material that just spilled, and it has 250 millimeters mercury, then you will say, wow, it's a way higher vapor pressure than water. Now let's look at the other one, acetone. Does everybody know how acetone vaporizes? It readily evaporates, right? And it has a vapor pressure of 182 millimeters mercury at 20 degrees centigrade. All the time vapor pressure is also measured at certain temperatures, okay? Because the higher the temperature, the higher the pressure of the vapor molecule that it exerts on the liquid phase, all right? Next, sulfuric acid, 65% is 1.6 millimeters mercury. So that's all you need to those are the only numbers for vapor pressure that you need, okay? As a CUPA inspector, you come across an MSDS, and you look at the vapor pressure, right away, it will tell you if it can vaporize readily or not. How do I put this in my mind, in my memory? Water, you just round it off to 20, and acetone is 200, and sulfuric is 2. So 220. Those are the only things that you need to remember for vapor pressure. If the vapor pressure is above 200, it's behaving more like acetone. If it's around 20 millimeters mercury, then it behaves like water. And if it is like 2 or lower, then it's not going to vaporize at all. It's going to stay around there. So those are the things that you need to understand for vapor pressure. The next property of matter that is usually confusing to CUPA inspectors, maybe because the books out there are also confusing, is its specific gravity. Okay? Specific gravity is unitless. Okay? I know to some of you this is already a review, but bear with me. We're going to go to the more exciting part. It's a ratio of densities. It compares the density of a liquid or a gas to a reference material. All right? For liquids, the reference is, of course, water. Water density at 20 degrees centigrade, you see the 20 degrees is right there again, because it's at room temperature. The water density is at 20 degrees centigrade is 1 gram per ml, per milliliter. And of course, everybody knows 1 milliliter is 1 cubic centimeter. 1 cc is equal to 1 ml. Or it's also equal to 8.34 pounds per gallon. Now this is where the confusion part comes in. Why? Because some books, they just put in density equals 1.8. And you would think that that is 1.8. It could be 1.8 pounds per gallon or this and that. It doesn't have any unit. But it actually is the specific gravity that they're giving you. 1.8 is the specific gravity. It doesn't have a unit. But then they put it on the book, density. Does anybody know about dangerous properties of industrial materials, DPIM, by Sachs? They put density there, and then they put 1.8. But it's actually a specific gravity, okay? So don't, if you want to convert it to pounds per gallon, you have to multiply it by 8.34. 1.8 times 8.34, it'll give you an idea of how much it weighs per gallon. Oh, by the way, for fire inspectors, are there any fire inspectors here? Good. I can make fun of them. I'm sorry. For fire inspectors, they have an easy way of estimating the weights, because they just use, instead of 8.34 pounds per gallon, they just use 10 pounds per gallon, which is a reasonable estimate. Okay, so if I have 5 gallons of stuff, I'll say it weighs around 50 pounds. Okay, 5 gallons of liquid. Okay, but of course, if it's sulfuric acid, it's going to be way heavier than 50 pounds. But that's just a quick way of estimating the weight. For gases, the reference is air. Okay, so air density at 20 degrees centigrade is 1.21 gram per liter. Okay, per liter. 1 liter is 1 cubic decimeter. Okay, or 0.075 pounds per cubic foot. Keep in mind these units here, they're not the same, okay? They're not the same. So in your hazmat calculations, keep that in mind. I already said this. Some MSDSs list the specific gravity as the density. Also for gases, sometimes they also put density, and it's actually specific gravity, because they put it, say, 2 point something, 2.5, like chlorine. Chlorine gas, I think it's like 2.5 or 3.0 as the density, but it actually is the specific gravity. Now, for gases, look, for water, it's easy, because in gram per ml, whatever the specific gravity is, that's also the density in gram per ml. But for gases, you have to multiply it by 1.21 gram per liter, okay? So, just something to remember. Now, another property of matter that maybe might confuse you, because it has the word specific. The specific volume is actually a volume per unit mass, the inverse of density. Okay? But normally, just in case you get confused with specific gravity and specific volume is the inverse of density. Okay? Now, when we talk of the elements, we have to discuss the periodic table. And I know, this is very elementary, I know. But hey, I have to show you the periodic table like that, you see? The elements are arranged according to increasing atomic numbers. And the atomic numbers represent the number of protons in the nucleus. And atomic weight is the weight of 1 mole of that element, okay? And 1 mole is representative of the Avogadro's number of atoms in that mole, okay? What's the Avogadro's number? Nobody knows. It's okay. CUPA Inspectors, you don't need to know that. The Avogadro number, I mean. But for the periodic table, we have the family versus the period. The family is the vertical, the column. So you have the halogen family, you have the alkaline earth family, you have the noble gases, and so on and so forth. And the period represents the rows. The row represents the number of electron shells in that element, okay? Very elementary. Oxidation states. This is very important, because you need to know how elements react with each other, okay? Oxidation states are the charges the ions carry. They're positive or cations or negative anions. The free elements these are things that you need to really remember and be familiar with, okay? If you're a CUPA inspector, you need to at least get a few things in your memory, because no matter what they say, chemistry actually plays an important part in your job, in hazardous materials management, in hazardous waste management. Free elements carry 0 charge. So, oxygen in air, it has 0 oxidation state. Chlorine gas has 0 oxidation state. It doesn't have a charge, all right? The charge that it carries when it combines with other elements depend on the group in the periodic table or the family. It's actually group or family, right? Halogen family carries a -1 charge, and alkaline earth family, the alkaline earth family, which is in group 2, will have normally will have an oxidation state of +2. Some elements may exhibit more than 2 oxidation states, which actually confuses a lot of the CUPA inspectors as well as me, because like for example, sulfur. Sulfur can carry a lot of different oxidation states. It can carry +2, it can carry -2, -6, and so on and so forth. So it depends on how it combines with other elements. Now we talk about the compounds. Remember the subdivisions of the matter? We started with elements, right? We're done with elements. Can you imagine? Now we go to the compounds, right? And then we're slowly going to the different other subdivisions of matter. The compound is formed based on the octet rule. The octet rule is the rule of 8, meaning they want to copy what the noble gases have. The noble gases have 8 electrons in the outermost shell. So if chlorine has 7, it wants 1 more. So it can get 8 in their outermost shell. So that's the octet rule. And the same thing with, say, sodium. Sodium has only 1 in its outermost shell. So it wants to give it up so that it can just have the octet configuration. Bonds may be ionic or covalent. Everybody knows that. Ionic is the transfer of electrons. So covalent is sharing of electrons. Okay. There are rules in naming compounds. You see, as CUPA inspectors, we need to be familiar with the material that we're going to inspect, right? If you're doing hazmat disclosure or inventory or things like that, when they give you a name, at least you have an idea. Is this an organic compound? Is this a salt? Is this really dangerous? Is this really hazardous? Or things like that. And that's what I'm trying to point out here. Because, for example, the vapor pressure. Now you know. If the vapor pressure is 300, then it behaves way higher than acetone. So it will evaporate right away. And it's the same thing. Here, there are rules in naming compounds. All you need to be familiar with the compounds that you're going to be encountering as CUPA inspectors. Organic compounds follow the sequential prefix. Meth, eth, prop, but, etc. And I know organic chemistry is really a hard subject to discuss, but all you need to know is that if you find any of these sequential prefixes, meth is for 1 carbon, eth is for 2 carbons, so on and so forth. If you see something like that, then it is an organic compound. What is an organic compound? It's anything that has carbon in it. It's a hydrocarbon, okay? Meaning it came from living things, organic, all right? Like when you buy at Trader Joe's, they're organic, right? The vegetables. Anyhow, listen. My wife always says, "Oh, will she see this? By the way, oh, forget that. Scrap that." Number 2, root names of organic compounds based on the longest carbon-carbon chain plus the functional groups. Everybody knows that, right? So you will name the compound based on the longest straight chain of carbon-to-carbon bonding. And that's plus the functional group. The functional group is like the nitro, the chloro, fluoro, the halogen family, and so on and so forth. Inorganic binary salts end in IDE. Like sodium chloride. Sodium chloride, when you see something with an IDE, it could be a salt. It might be a salt, or it's definitely a salt. One of those things. So you're just familiarizing yourself with, when you look at the inventory, I see that there's an IDE at the end. Could be a salt. It could be an organic salt too, because it might be connected with a meth, something like methyl chloride. That's a salt, but it's an organic salt. All right? Oxysalts end in ATE for the normal ion. Per 8 for one more oxygen atom, ITE for one oxygen less, hypo ITE for two oxygen atoms less. The most common example for this is the chlorate ion, oxysalt. So chlorate, sodium chlorate, is ClO3. Okay? Now, if there's an additional oxygen in the ion, ClO4, then it will be sodium perchlorate. And we will learn about that later when we talk about reactive chemicals, all right? For one oxygen less, it becomes sodium chlorite, CHLORITE. But if there are two oxygen atoms less, which is ClO, it's hypochlorite. Calcium hypochlorite, sodium hypochlorite, which is bleach, all right? NaOCl, or actually NaClO. Everything still okay? Are we zooming past chemistry very fast, or okay, or very slow? Well, tell me if it's very slow. Tell me. I'll speed it up even more. Solutions. Remember we talked about elements, the periodic table, right? Then what's the next subdivision of matter? Compounds. We did that. Oh, we're done. Now we're going to solutions. Solutions, solute versus the solvent. Solvent is the dissolving medium. Solute is the dissolved medium. Remember we talked about the suspensions. The suspensions are this, there's a suspended particles. Thank you. He said suspended, so I heard it. Suspended, the particles are actually still there. For example, what's the most common? I told you about the hazardous material that's a suspension, which is printing inks, right? Printing inks. What's the most common thing you buy at the grocery? It's a suspension. Anybody? Milk! Who said that? Congratulations, 50 points for you. Milk is actually a suspension, all right? Now, in a suspension, the solid actually still exhibits its characteristics. It's still a solid, all right? It's just suspended around in the liquid, like the milk, the butter fat. Butter fat. I don't want to insist on that last portion there because my wife is going to kill me. Anyway, they're just suspended in the medium, right? Whereas in a solution, the solid does not exhibit the characteristic of being a solid anymore. Like sodium chloride dissolved in water, a salt solution, the solid is not there anymore because it breaks down. The water molecules surround the ions of the cation sodium and the anion chloride, the chloride ion, okay? So solutions and suspensions, what's the difference? You know that it's suspension. Thank you very much for coming, sir. I understand that you have other things to do. Okay. So the solvent, for solutions, it's actually, it doesn't exhibit any of the characteristics anymore. Okay, that's the solution, like hydrochloric acid solution, phosphoric acid solution, so on and so forth. So that's the difference between solution and suspension. What are the types of solutions? The types of solutions are based on the solute and the solvent. It could be a solid in liquid, a liquid in liquid, liquid in liquid solutions, all your petroleum products. All your petroleum products, most of them, they're all just solutions because they're just mingle around together, you know, like gasoline and so on and so forth. You see, you cannot say that gasoline is a heterogeneous mixture because if you take a portion of it on one side and then take another portion of it in another side, they're actually exactly the same. It's a solution of liquid in liquid, okay? Gas in liquid is carbonated water. Everybody drinks soda, okay? So that's gas in liquid. Solid in solid, like any of the alloys, metal alloys, okay? Now we go to hazmat calculations, expressing concentrations. This is normally what CUPA inspectors deal with. You are actually involved in trying to determine how much material is actually in solution or in the room or something like that, okay? So we go to the expressing concentrations. Calculations in hazmat chemistry. Whoa, that's a big deal. Calculations in hazmat chemistry involves concentration of contaminant in the environment or of a solute in a solvent. You know, like you go in a room and then you go to a plating shop. You go to a plating shop and then you experience some kind of like sore throat, or you smell some kind of bad odor, then you want to know what the concentration of the contaminant is in the environment, right? And that's what calculations hazmat chemistry is involved. Percent concentrations by weight or by volume. MSDSs give the percent concentration by weight. Oh, you did not answer. I was looking for you to answer that question. But what's your name, ma'am? Sharon. Okay. And you're from Sacramento County. Welcome. Percent concentration by weight. MSDSs usually give percent concentrations by weight. All right. So if they give you percent concentration, normally it is by weight. Actually, in chemistry, there's like an understanding that if it's a solid or a liquid, and they did not specify whether it's by weight or by volume, it's assumed to be by weight. If it's a gas, it is by volume. Because ideal gas behavior, by percent by volume, is actually percent by mole also. Okay? Again, to some of you, percent by mole, percent by mole. It's okay. But to some of you, whoa, wow, this is so elementary. Why am I here? Okay. Percent concentrations by weight is definitely just like this. Weight of solute divided by the weight of the solution times 100. And then percent by volumes, of course, volume of solute divided by volume of solution times 100. But then the volume, as I said, for gases, it can also be mole percent. It's also the same as mole percent. Molarity. This is very important in the expression of pH. Okay? Everybody, CUPA inspectors, come on. You know pH, right? 0 to 14, anything below 2 or equal to 2. Correct me if I'm wrong. If there's an equal there, becomes equal, or is there an equal sign to become hazardous waste for corrosivity, characteristic? Okay. Anyway, okay, equal or less than 2, that's the pH. Then that is a hazardous waste, right? But the molarity is actually the moles of solute per liter of solution. Moles of solute. Moles. What is moles? Moles is actually weight over molecular weight. Everybody knows how to calculate for molecular weight, right? You just need to know the number of atoms in the compound and then multiply it by their corresponding atomic weights. pH is the negative. You see, the thing, as I said, the molarity is important in the expression of pH because it's the moles of solute per liter, right? Now, I'm sorry. I should use this. pH is the negative logarithm of the hydrogen ion concentration expressed in moles per liter. All right? Keep that in mind. It's expressed in moles per liter. It's not expressed in any other concentration, percent by weight or percent by volume or whatever. It's supposed to be moles per liter. So you need to know the molarity if you want to calculate. But normally, do you need to calculate? No. We have pH paper, right? All right.